All right, so it's a pleasure to introduce Professor David Masser. So I'll say a few words before we start. So David Masser received his education in Cambridge, obtaining his PhD in 1974 under the supervision of the Fields medalist Alan Baker. His first employment was at the University of Nottingham and the University of Cambridge, becoming then professor at the University of Michigan and then at the Universität Basel, where he also served as chairman, and he has been supervisor of 12 PhD students. He had visiting appointments at several prestigious centers, including IHP and IHES in Paris, the Max Planck Institute in Bonn, IAS in Princeton, ETH, and the Massera in Berkeley. He was invited speaker at ICM in Warsaw, and he served in the number theory panel for ICM in 2010. He's a fellow of the Royal Society and has been editor of the Michigan Math Journal, Illinois Math Journal, and the Krells Journal. His research mainly regards transcendental number theory, Diophantine approximation, and Diophantine geometry. And the ABC conjecture, originated by Professor Masser and Joseph Oesterle, is one of the most famous and emblematic current conjectures of number theory in the Diophantine field. Among others, his isogeny theorem with the Wüstholz for abelian varieties has also several fundamental applications. Okay, thank you.
Thank you very much for the invitation and the very welcoming introduction. So I'm heard, yes. I got the green on, yeah. It's always nice to come back to Pisa. I try and come every year. In 2005, I gave a lecture at this colloquium. And this was had this title, starting off with something relatively simple and ending up with something relatively complicated. So an alternative title for the present talk could be from log 2 to generalized Jacobians. Log 2, so we start off with log 2, and log 2 is simply the integral from 0 to 1 of dx over x plus, right, 1 plus x. So there I've begun, and now I've got to work my way in 50 minutes to these things. The actual title was Transcendence of Algebraic Integrals. Algebraic integrals, people have been trying to integrate various functions since the differential calculus, so that's kind of prehistoric and very extremely classical. Transcendence is also a little bit more classical than is often thought. One often says that it began in 1844 when the existence of transcendental numbers was proved by Liouville. But in fact, if you go back, I didn't go back into history, but Gisbert Wüstholz went back into history and found that around about 1690, or there's a precise date, 1691, there was some discussion between Leibniz and Huygens about whether certain areas could be transcendental or not. Now, you can read this in also a Colloquium De Giorgi by Wüstholz, 2009. And the subject of their correspondence was whether certain areas are transcendental or not. So one can consider, for example, a circle. So x squared plus y squared equals 1. And then the area, say, so this would be this area here. If you take the positive square root, And of course, this is transcendental. This is pi over 4. But it wasn't known to be transcendental then. Its transcendence was only proved in 1883, so sometime later, is transcendental. But they didn't know that then, and the interest then was that you don't always get a transcendental number here. If you make, and what Leibniz did apparently was make a small adjustment to this, and if you now take the integral, so you put an x in here, and now if you interpret that also as a integral, then now the equation is y squared equals x squared 1 minus x squared. So this factor comes in there. And this looks rather different from the circle. In fact, this looks like this. This is, I'm not an artist. This looks like a terrible singularity. It's not that bad. And this is 1, this is 0. And you can ask the same question. And of course, now you can you can see that this is not transcendental, and this is comes out to 1/3. So Leibniz said you can just modify this and get away from something transcendental. This looks like a lemniscate. I don't think it's called a lemniscate. There's a more famous lemniscate in the history, and that's has this equation. And it looks pretty much the same. Slightly better drawn now, but it looks pretty much the same. And if you now want to, you can ask about the area again. And if you, so the relation between solving this for y is not very easy. It's rather cumbersome. And it's quadratic in y squared, so you can do it. So you can write down an integral. And if you give this to a computer, say using Maple, it will refuse to answer. It will just tell you, it will just repeat what you asked it. So, but if you do it numerically, it comes down to 2.250. This is the first example in my abstract. It comes down to 0.250 as stated in the abstract, and then if you can get how many places you like. And so this is, again, I'm talking about this part and this part, and this is probably 1/4. It's not so easy to see that. Requires a bit of calculation. I don't know. This is I Googled transcendence this morning. I've never done that before, because when I started, Google wasn't around. And it was interesting. In between here and here, somehow the idea of transcendence got crystallized. So in between here, Lambert, this French mathematician, conjectured that pi and d were transcendental. So it kind of, and then by here it was established, and then the first actual natural transcendent result of E, that E is transcendental, was Hermite then. So I don't know. It would be interesting to find out. So this goes back to Fagnano, I think the father, there are two of them. I think this is the Count. And he was not interested in the area at all. He was interested in the length, the perimeter. And then the integration problem there is more complicated, and you can't do it in elementary terms, and this led to elliptic functions. So what kind of equations are we interested in? So f x y equals 0. And they all look algebraic here. If we allow non-algebraic functions, for example, y is e to the x, then the integral 0, 1, e to the x dx is e minus 1. And so by the Hermite, result is transcendental, and that's because you used a transcendental number in the equation. So this kind of thing you better ignore. But even if you look at y equals e times x, then the integral y dx is e over 2. So you get the same kind of transcendence coming from the transcendence in the equation. So we disallow these, and so this is going to be f x y is in q bar x y, where q bar is the set of algebraic numbers. So it's better we start off from the algebraic numbers and then ask about transcendence. And this set of numbers usually we look at them as complex numbers, not just abstract extensions of the rationals. And areas, by the way, come in other kinds of problem, counting, how many count the number of points in the circle of radius square root of n, integer points there. And everybody knows that an approximation is obtained by the area. The number here is approximately the area of this, and the error term is usually the length. So we get the area and length coming in. So the area, if you look at the whole thing, then it should be pi scaled up by this radius squared. So it should be pi n plus terms of order n to the half. So there it's an easy kind of connection here. If you look at something more, if you look at this kind of thing and you step up the degree, x cubed minus 2y cubed less than or equal to n, then the problem changes somewhat. What's the analog here? The analog here, now this minus makes problems. You can go off to infinity. This, and you have an asymptote, but the actual shape of, well, if I draw the boundary here, the boundary of this, it comes down to, now this, something like this. So you're asking for the number of integral points in here. And now the area is finite. you have to check it doesn't, you have to check that. You need to check the area is finite, but the perimeter is infinite. So this general principle here, area plus perimeter, or the error with an error of perimeter is no longer valid. And even the finiteness of the number of points here lies very deep. Nevertheless, Mahler got an asymptotic formula, and the formula is a n to the 2/3 now. X and y may go up to n to the half if you ignore the cancellation, and so you get n to the 2/3 there, plus an error term, and this a is square root of 3 times gamma and this is transcendental by Siegel, 1932. So we'll see this number later on. And then a little bit of a digression. More generally here, you can look at f, x, y, at most n, where f is a form, usually over the integers. And Mahler showed that the same asymptotic behavior, this would be 2 over d, if d is the degree of f, plus an error term. No, but up to a year or two ago, no one seems to have asked if this number is transcendental. This is known to be transcendental. The transcendence of this seems to be still open. I could prove that it was transcendental provided four does not divide the degree, and it's probably always transcendental if you take the degree at least 3. So rather easy looking problems where you can do the error, you can do the counting, but you don't still know the transcendence. So that's enough about area and motivating and counting, motivating the the algebraic integrals. I'll make a short list now of these things. Here is the first one. So this was exhibited this, so this is easy to calculate. Siegel didn't, that wasn't the achievement of Siegel. Siegel asked if it's transcendental, and Baker, 1967, replied, yes. Integral 0, 1. Let's put a square root in. This is 2/3 of this A, and so this is transcendental. So if I change the sign there. If you ask Maple this, it gives you quite a lot of rubbish. It tells you the answer, but it uses elliptic functions which are not Weierstrasses, Jacobi elliptic functions, which are known to people who build bridges and things like that, but they're not. It's not very easy to read off the transcendence. So this gives you Maple rubbish. But in fact, it's transcendental. Schneider. Integral 0, 1 dx, 1 plus x, 1 plus x cubed. Worse rubbish. And there's no name really here to be attached to it, but I shall mention Fustolz again soon. Then integral 0, 1 dx over super rubbish. As long as half a page of strange functions. And then for this integral here, which I write up again, it was in the abstract. This is square root minus a half plus x squared plus square root 1 plus 8 x squared over 2 dx. And then make, as I said, Maple just can't do that. Okay, so let's now get some system into this. We have an algebraic curve here, and we assume that f x y is irreducible over q bar, and then it defines an algebraic curve, say C over q bar, and an irreducible algebraic curve. So this has a genus. And the complexity of the problem usually depends on how high the genus is. So genus 0, you essentially have a sphere, which is or C or P1C. You're working essentially on this. Genus 0, genus 1 is then the torus, and then genus 2 has 2 holes and so on. So I'm going to restrict in this talk to genus 0 and genus 1. The genus 0 and genus 1 don't simplify the F. The F can still be very complicated. F can have degree 100, but it's genus 1. There's no connection, no good connection between the genus and the degree. So then Then you could look at integrals like y dx. Or you could, that was just for area with the y there, but it's better to allow any function on the curve. Nothing. We've dropped all interest in area now. So this is some rational function of x and y over q bar, or you can just take a differential omega on the curve defined over q bar, and then a path. And here the area was from A to B, but here it's better to take a contour, and the contour goes from some point A to some point B. So on the here you may have a point A and a point B, and then you go from A to B, and that's the gamma. And you assume that the omega can have poles now, and so you assume that the poles don't lie on this curve, so there's no, as you go along here, you don't blow up. And then one insists, so gamma on C from A to B, A from B on C defined over Q bar. Everything, all the data that come in have to be related to Q bar and normalized, and otherwise you get from the beginning transcendental numbers. You don't really care if the equation defining the path is defined over the algebraic numbers or not, because the path, the actual path is not so important. If you change the path like that, the integral doesn't change. But the main thing is the endpoints. If you change the endpoints slightly, then it will change. So the basic question here is then, Q is I transcendental or algebraic? And there were lots of, well, in the history, the various examples considered: Siegel, Schneider, Baker, etc. The first really general result was due to Wustholz. 1986. If gamma is closed, so closed means A is B, then the integral can be algebraic. For trivial reasons, you can have a contour of length 0, not going anywhere, just staying there, and you get 0. And then, but if this happens, then the actual value is 0. So this is very useful in applications. If you're looking at a perimeter or an area here, the perimeter or an area is usually not 0, otherwise you wouldn't be investigating it, and so you get the transcendence straight away, or closed paths. So this is pretty conclusive for closed paths. And these things are usually called periods, but I want to avoid this word because it's overloaded recently. There's several different senses of the word period now, and I can't keep them apart, so I don't use this. But the point is that gamma is closed. Sorry? No, this is general gene. Yeah. Actually, all the integrals I've written up so far, gamma is not closed. So you have to be lucky to apply this in some sense. So the case of non-closed gamma had to wait had to wait quite some time. This was Annette Huber with Gisbert Wustholz, and this is a book, 2022. And the book contains many results, many new results. I won't quote any of them in this lecture. They certainly deal with non-closed paths, so that means there's no restriction on the path anymore. They introduce a motivic point of view into their proofs. But although there are many new results in the book, I don't see in the book any consideration of any simple way of telling if it's transcendental or algebraic, at least in an effective sense. So we want effective Q. How can we actually do it? Yes. Oh no, if it's closed, well, we can say and there and this, then I must be 0. It's related to the number of the singularities in a yeah, it depends if the curve is plane or not. So there is a relation, but it doesn't help with this talk. So now I'm just going to I'm going to go to the effective part. For a function g on C, this curve, so I stay with an arbitrary curve. And gamma from A to B with GA is GB. So this function starts off at this value on the contour, and as you go along, it's the same value at the end. One defines n gamma g to be this integral. So there's a differential, sort of typical differential of the third kind. And 1 over 2 pi I. And these integrals, for me, they count as being known because they're integers. These are integers because informally, if you integrate dg, this is d of log g. And so this is 1 over 2 pi I log g. So you're from A to B. So this is log GB over log GA, where log, you don't know which log. But if you choose the wrong log, then the indeterminacy is kind of cancelled out by this. And so this is certainly going to be an integer. So to calculate this, to find out whether that's transcendental or not is child's play. Just calculate it to within a half. And if it's not bang on an integer, then it must be, it can't be algebraic. And the question here about the effective Q was actually answered in genus 2 by van der Poorten in 1976, I think, 1971 even. So now genus 0. So we go back to the general question. We're now in genus 0. We're on here, for example. And in effect, what you're integrating is rational functions of a single variable between two complex limits. So it's more or less this kind of setup there. You can see very clearly what you're doing. And in fact, every omega has a special form. It can be an exact differential, but that doesn't exhaust all of them. Otherwise, there'd be no fun in integrating. And then C1 and then it's a combination of these kind of logarithmic things. So this is related to the partial fraction expansion of rational functions, but it goes into the literature back to Liouville, and this is called an elementary differential. This is called here elementary. And Liouville did. It's the same Liouville who worked on transcendence. He proved some remarkable results on things of this form. And Umberto and I wrote a paper recently on other aspects of this thing. So and extremely convenient to take the number here of terms P minimal. If you don't do this, you get completely lost. There must be a minimal. And then van der Porten's result is as follows. Again, genus 0. I is algebraic if and only if so now we have this decomposition and there's an effective way to tell whether it's algebraic or transcendental, and it's algebraic if and only if G1A equals G1B, GEA equals GEB. And these winding numbers are all 0. This is C, in which case what is the integral? In this case, when you integrate these things, you get more or less integers, or well, no, not quite, no. But in which case, anyway, the integral is obtained by just integrating this term, and yeah, well, the winding numbers are 0, so you get zeros here when you integrate, and you only integrate df, and so you get the difference in values there, which is then algebraic. So we can do very quickly Fagnano. The lemniscate has genus 0, but it's not obvious from the equations. E.g. the y dx that gives you the area turns out to be d of minus xy cubed over x squared minus y squared. So it's just a df. And now you can do the integration. You have to be careful with this. There's a singularity there, which means you have to make a limiting procedure, but you get the area is 1/4, as Maple refused to say. And behind this is Baker's theorem, which I don't state in general. If you don't have these kind of things, then you're liable if GB is not GA, as in the conclusion, then this logarithm can be a log 2. You're back to log 2, and you can have a log 2 there and a log 3 there. So you have a linear form in logarithms, and in fact, these C's are linearly independent over the rationals. That comes from the minimality. So you get a linear form in logarithms, and Baker knows how to control that. So that comes from Baker's theorem. Van der Porten didn't define these winding numbers, but I think this makes things clearer. So probably I have really only about 2 minutes left or 3 minutes left. So I don't am I? So I took this a bit further and I did a version in genus 0. I don't think I'll state it here. It involves some more kind of winding numbers. In genus 0, you no longer have this special form. Not everything is elementary, but you have a related canonical form. Omega is now, sorry. Sorry, yeah, genus 1, yeah. Then you have, worthwhile writing down. Here I've reduced to standard Weierstrass form. So a curve of genus 1 is always isomorphic to one of these Weierstrass equations. That enables one has an independent variable x, but the non-independent variable is simply related in this form. So you have a kind of version like this. And theta p is 1/2 of y plus eta over x minus psi dx over y, where p is on C. So it looks completely different from this, but it's the best you can do. And oh, I need coefficients in here. And then you can define a similar winding number. And gamma p as 1/2 pi I integral when gamma is closed and homologically trivial. And this is also in Z. It's not so easy to see that. That depends on the special nature of this thing. But you get another winding number. And then the theorem for genus 1 says essentially I is algebraic if and only if either this does happen, which is not expected, and then with these, and then you get that. So that's a special case, but it's unlikely. If not, then you get a condition in terms of these winding numbers. And so you can very easily determine, answer the question Q in genus 1. And I didn't make it to generalized Jacobians, but a generalized Jacobian comes from the group varieties that you use to prove all these things. For Baker's theorem, you use rather simple looking group varieties, but for the more complicated things, and for genus 1, you need some things which can be obtained by generalized Jacobians. Okay, I'll stop now. Thank you.
Okay, by effective, you mean that when the function is given and the contour is given perhaps by some parameterization?
Yes, if you know the parameterization, you can then work these out numerically and find their values.
So you can answer effectively the question whether the thing is transcendental
In genus 1, yeah.
in genus 1.
In genus 2, the generalization of the theorem is false because the Jacobian might not be simple. And but if the Jacobian is simple, there's probably an extension to genus 2. Genus 3, I don't know about. It gets shaky. Well, I was wanting to illustrate that, but on the so this is homologically trivial because you can
Homotopy to a point.
point, yeah. But if you go round, if you go round like that, then that's
Okay. So homotopy to a point. Okay, I got that.
Yeah.
And the statement is now it is algebraic if and only if this new integral that you define is 0.
there's it's algebraic if and only if either either this happens and this happens, or if gamma is I said it, but I didn't write it down. If gamma is closed, homologically trivial, and then you get I equals 0, and there's another condition on the winding number and residues. So I didn't write this down because of time.
Yeah.
But now I could say a bit more. Yeah.